How about now? Can you still see this?
Yeah.
Okay, I'll try again. Can you still see that?
Yeah, now it works.
Oh, okay, great. As I was saying, admittedly, this is a work in progress, and a lot of the ideas may come across as a bit half-baked. And if you want to follow our progress, then the GitHub repository there contains all of our current code, and that will be gradually updated over time. The other reason why this is going to be quite a strange talk is because I'm going to talk about two things that aren't admittedly talked about often within the same sentence. And the first of those is theorem provers. So here on the left-hand side, you've got a schematic diagram of the typical system organization of what's known as an LCF-style theorem prover. Now, Isabelle, Coq, Hall4, Hall Light, all these systems are LCF-style theorem provers. And kind of the unique aspects of these systems is that they're organized around a privileged system component called the kernel. So this kernel is privileged because it's the only system component that's actually able to authenticate a system, authenticate a theorem as being legitimate. So this kernel is written in a programming language, typically some form of ML, for example, standard ML or OCaml. That language is typically called the meta language of the system. And the kernel is just a library within that programming language. And the kernel exposes an API, just as any other ML library would do. And untrusted automation that's linked against the kernel and logically sits outside of the kernel and drives the kernel to produce theorems, makes use of this API to produce a theorem. And this is how they communicate across this API. On the other hand, desktop operating systems are also organized around a privileged system component called a kernel. In this setup, a kernel is isolated from untrusted user space code by a hardware privilege boundary rather than a programming language module. So the kernel will use things like memory protection and hardware isolation levels and so on, variously called exception levels or privilege rings, to essentially protect itself from untrusted user space. And what's interesting is that the kernel could be written in one language, for example, typically C, but the untrusted user space is typically written in a lot of different languages. And it doesn't necessarily have to follow that the user space code that's interacting with the kernel has to be written in the same language that it is. What matters is that they can both communicate with each other across a system interface, which is a binary interface consisting of various things like system calls and an associated calling convention and various agreed upon error codes that the kernel exposes. Okay. Now, if you squint quite a bit, at a high level of abstraction, both an LCF and a desktop OS kernel are both trying to maintain very similar things, namely important system invariance in the face of unbounded interaction with untrusted code. However, the mechanisms by which the two types of kernels isolate themselves or protect themselves against these system invariants being undermined, be it they could be the logical soundness of the system in the case of an LCF kernel, or some sort of important security property in the case of a desktop OS kernel, are very, very different. So as mentioned, LCF kernels favor isolation using type abstraction and programming language module boundaries. And here, the system soundness ultimately follows from the type soundness and the ability of the meta language to correctly abstract the type of theorems. On the other hand, desktop operating system kernels favor all the hardware-oriented things that I was talking about before, things like memory protection and exception levels. And ultimately, system security follows from the kernel being able to correctly isolate itself using all of these tools provided by the hardware. However, at this point, we can ask, what would happen if we organized a theorem prover to look more like an operating system kernel rather than a typical LCF kernel? And essentially, that's what we've been investigating with this Supervisionary. And that's what I'm going to talk about next. And most of this stuff is actually implemented in our GitHub repository. We've got a few things left unimplemented, but the majority of the kernel is actually there. And if you look at the repository, you'll see that Supervisionary is a prototype proof checking system for Gordon's Hole, implemented as a WebAssembly host. So we're not actually implementing a real operating system. That would be kind of over the top. We'd have to deal with all sorts of things like booting a real machine and so on. By using WebAssembly, we essentially get an instruction set and an ability to kind of act as an operating system to programs written in that instruction set, very similar to a real operating system without all of the fuss. So the WebAssembly program that is executing kind of under supervisionary supervision still communicates with the supervisionary kernel using a system call like interface. And what I should say is, although we have implemented supervisionary for Hull, most of the major ideas here will follow over to other similar kind of logics, things like dependent type theories or first order logic and so on. I don't think there's really anything inherent, apart from some of the particulars of the system call interface that I'll present later, that's inherent to Hull. So what's interesting about supervision is that it's implemented in Rust, and this is a very unsafe programming language. And this is a far departure from the typical kind of meta language of LCF, which, as I said, is this type-safe functional programming languages like ML and OCaml. However, unlike in LCF, we're not actually going to be using any of the programming language features that like the modules and the type safety and so on to kind of protect supervisionary. And really, this choice of implementation language doesn't pose any sort of risk to system soundness as long as we carefully design our system interface. And on that point, the supervisionary system interface is quite interesting. It's quite a big departure from the typical LCF interface. So essentially what supervisionary does is it maintains a series of kernel heaps, and you can think of these as private memory spaces of the kernel. So these are things that only the kernel, the memory areas that the kernel can manipulate, and they contain various kernel objects. And each one of these kernel objects is pointed to by a kernel handle, which you can intuitively think of as being akin to a pointer that points into one of these kernel private memory spaces. Now, each one of these kernel objects corresponds to one of the kind of the usual paraphernalia of a typical kind of theorem prover implementation. So we've got objects that correspond to things like type formers, types, constants, terms, theorems, and so on. And each one of these things in that list that I've just mentioned builds on previous concepts earlier in the list. And when the kernel boots, so to speak, these memory spaces initially contain various primitive kernel objects. And these correspond to things like logical quantifiers and connectives and various other like primitive theorems. And the also, for example, the type former for the function space arrow, which is very, very primitive in Hull. So these are all pre-provisioned into these kernel heaps when the system starts, and various handles are already known, and they have to be agreed on between user space and kernel space that are known to point to these primitive kind of kernel objects. Now, importantly, as I said, these kernels, the kernel heaps are private, and what like a key system design aspect of supervisionary is that the content, these kernel objects that reside in the kernel heaps, are never directly exposed to untrusted code. Rather, the kernel is going to act on behalf of untrusted code in manipulating or querying or creating them in via handles that are passed through system calls. And the kernel acts on behalf of untrusted code. And another thing to note is that now these kernels are essentially the ground source of truth in the system. So as if you imagine interacting with the whole light kernel or the whole 4 kernel, you know that something is proved. You know a theorem exists when you're able to hold on to a non-bottom element of type them within the system. However, in supervisionary, you know a theorem exists. You know you've successfully proved something when you successfully hold on to a handle that points to a kind of a corresponding theorem object within the kernel's heap. Okay, so how does like the syscall interface look for supervisionary? First, if you recall, the kind of the recursive grammar of whole types, or if you've never seen it before, this is it on the slides. It's very simple. Whole type is either a type variable, which I'm using alpha here to range over, or it's the combination or the application of a type former ranged over by f to a list of types. And f is said to have an arity, which is a natural number, which describes how many type arguments f the type former is expected to have. So, for example, the function space type former has an arity of 2 because it accepts a domain and a range type. Okay, so to create a new kind of type former combination, as just discussed, we have a syscall type.register.combination, and it takes 3 arguments. So the first argument is a pointer to or is a handle that points to a registered type former in the kernel's type former heap. And the second one is a list of kind of handles to existing types, also in the kernel's type former heap. Whereas the final argument, sorry, is a pointer into the WASM program's own memory, which will contain the result, if successful, this syscall produces. Now, on the left-hand side, we kind of see the before stage, before what's assumed before that the syscall is invoked. And we see here that, for example, this handle f in blue is pointing to a registered type former, which has been registered with arity 2. So the syscall will first look that up. And if that handle doesn't actually exist, it's not pointing to anything in the heap, it will fail with a kind of a noted error code. Otherwise, it will then go on to read 2 handles from the list, this orange T's list, and will then look up each individual handle in the type heap. And again, if these dangle, then the syscall will fail. Otherwise, it will invent a new handle name. It will register a new type combination here on the right. Down here, you can see the green handle is now pointed to a combination between f and ts1 and ts2, and r will then contain that new handle. Okay, and one thing to note here is that supervisionary has to be written very carefully. It has to maintain a key system invariant, namely the inductivity of its heaps. So what do I mean by that? I mean, if you see on the left, between ts1 and ts2, there's a grayed out box that contains another combination. So this isn't within the footprint of this syscall, but we can imagine it's there and it's not going to be touched by it. But it essentially already contains 2 handles, one pointing into the type former heap, so that's handle number 3, and another one in its argument list, the handle 0, pointing back into the heap of types. Now, those handles always have to point at some kind of pre-registered or already registered kernel object. They cannot just dangle. And moreover, if we do this pointer chasing, eventually that has to bottom out. Otherwise, a syscall may not terminate, for instance. So this is a key invariant that's maintained. So our syscall interface is quite extensive. There's, I think, on the order of about 75 syscalls at the moment. So I'm not going to go through all of them. I've not got time, but that is quite emblematic of all of them. It will give you a good idea of what they all look like. So now here is kind of like a schematic diagram of what supervisionary looks like. You see that essentially it acts like a normal operating system kernel in that it exposes a syscall interface across a WASM privilege boundary to the untrusted code. And this untrusted code makes use of a utility library called libsupervisionary, which you can think of as a bit like libc, that abstracts over the syscall interface and provides a higher level kind of set of abstractions to untrusted automation and proof state management code that might be driving the kernel. So libsupervisionary at the moment only really exists for the Rust programming language, but you could write one, for example, for C. And this is kind of a key point. Now, supervisionary itself doesn't really have a meta language anymore in the same sense that LCF does. So you don't have to write in ML, for instance, to kind of be able to drive the kernel to produce some theorem. Rather, you can produce, you can drive the kernel, you can write any automation in any programming language you want, as long as you're able to compile it to kind of binary compatible WASM code. So another quite interesting thing about supervisionary is the way that we might be able to kind of specify what the system call interface does. So I'll quickly skip over this because I've got one eye on the time, but essentially the way that I presented it in terms of like a pre and post state is very suggestive. And you'll see that we're passing handles or pointers all over the place, and essentially supervisionary is just a big exercise in pointer management. The natural way of kind of specifying pointer manipulating functions or programs is with separation logic. And for instance, we could do this for the entire syscall interface. So for example, theorem.allocate.reflexivity, which is a system call which captures the reflexivity axiom of Hall, takes as precondition that its first argument points to a term that's already registered in the in one of the kernel's heaps. And as postcondition, well, that term, that handle continues to point to that term, but then also the system call invents a new handle which out points to, and that handle in turn points to a sequence that essentially states that R is equal to R, as one would expect. And note here we should also handle all the failure cases as well. So we're really kind of paradoxically, failure is a type of success here, and that we don't ever want these system calls to crash. That would essentially be something like the blue screen of death on Windows, where your kernel just hits some sort of internal invariant failure and dies. Really, if there's something wrong with this input H handle, for example, it dangles, then the syscall should succeed, but it should succeed with an error code. And I think actually here why this is especially interesting is because it's a bit of a rejoinder to a body of work that tends to look at languages associated with theorem proving in terms of just functional programming. So if you think of things like VeryML, which I'll get to at the end of the talk briefly, and also LTAC and so on, they're all very, very functional. But here we essentially have a lot of syscalls which do memory allocation, they do freeing, and so on, and it feels much more imperative. I think that the natural language that you'd build around this, like a higher level language, would be imperative rather than functional. So now I'm going to quickly move on to a more speculative part of the talk, and I'm going to get onto something that's more, I think, relevant to PriSC. And essentially at this point, what we've got is a very strange proof checker. It's programmable, but the programs can only really manipulate kind of theorem objects or other kernel objects as discussed. They cannot do anything that you'd typically associate with a program, for example, query or manipulate the file system or generate random bytes or make any other kind of side effect for that matter, because they just don't have the functionality. Supervisionary hasn't exposed that to them. But we can ask, well, what happens if we do expose that via a new set of system calls? So for example, we could implement something like the WebAssembly system interface, which is a bit like POSIX for WASM, and then you would be able to manipulate files and generate random bytes and so on from one of these programs, in addition to being able to manipulate proofs and terms and types and so on and so forth. And once we have that, we essentially have two very separate kind of faces of supervisionary. We have the kind of the standard OSI face, which does all the file I/O and so on. Then we have the theorem prover face, which does all the proof construction and manipulation. And in a sense, now supervisionary is just a normal virtual machine in the JVM sense of the word. And you could compile a standard, for example, text editor or maybe some like Fibonacci program or whatever, write the result to a file, and everything should just work on top of supervisionary. But then we can also ask, well, what happens if we start to merge these two faces of supervisionary? And one way that we could do that would be every time that a program wants to make a system call, we could force via supervisionary to have that program pass a handle to a particular theorem as an additional argument to the system call. Because really supervisionary now is the only way that that program can have any side effect on the system via the file system, for instance. We can make it jump through whatever hoops we want to be able to do that. And in particular, the statement of this theorem that needs supplying, which I'll call a challenge, that could potentially change dynamically according to the runtime state of supervisionary itself or the executing program as well. And if you step back a bit, what this idea kind of turns into is the idea of handles to Hall theorems, turning into a form of capability. So in particular, if you can pass a handle to an appropriate theorem when making a system call, then that system call will execute as you'd expect, otherwise it will fail with a particular error code. And moreover, as supervisionary exists, the kernel, at a relative level of privilege, and by that I mean it can read all of the heaps of the executing WASM program. It can look at the system call name that was invoked at the point of invocation and the arguments. It can look at the content of the file system. It can also examine its own kernel runtime state and so on. All of this information can be used by supervisionary when formulating one of these challenges. So speculatively, I'm going to suggest one particular type that these policies, which are where challenges are derived from, could take. So here you can see a policy is a particular Hall type that takes, is basically a function from the reified program state to the system call info, the kernel states, and then that maps into the whole Boolean type. And you can imagine that all of these kind of three inputs to this function are Hall record types or similar that have lots of internal fields capturing bits of data. And then these policies can then be dynamically applied to appropriate Hall data to specialize it at runtime by supervisionary when it's kind of trying to produce a challenge. And now we can see that there's two particular policies, the lambda psk.true and false, that are quite interesting in themselves, because true essentially corresponds to no challenge or a trivial challenge, because true is always provable in Hall, whereas false corresponds to an impossible to satisfy challenge, because false, at least in a consistent context without any additional axioms, is never provable within Hall. And this is one way, for instance, that the kernel, the supervisionary kernel, could just cut off a system call and make it impossible to invoke from the executing program. But we can get much more interesting than that. So, for example, here we can limit with this policy. We can limit the program to only being able to invoke the fopen and the get_random system calls. But that's something that we can do with existing systems of capabilities. For example, Cloud ABI and WASI were very similar to this. They can do something like that. So we can become a bit more specific. So for example, if we're trying to invoke the fopen system call, then when we interpret the first argument that's passed to that system call as a path, when we take the bytes and interpret it as a path, then it must be the case that that path is equal to temp/foo.text. And again, that is kind of within the realm of existing systems of capabilities. But maybe if, for example, we were trying to write a file using the fwrite system call, and then when we looked up in the file temp_foo.text and we read some bytes and we interpreted those bytes as a real number y, and then we interpreted the bytes that we're trying to write to the file as well when we're invoking fwrite as a real number, and then we made sure that that real number corresponded to the least solution to some inequality, then that is something that we cannot currently do with capability systems. Essentially now we've got a very, very fine-grained level of capability, where capability is not merely phrased at the level of individual system calls, but at the level of correctness properties, for instance, where you can only write to a file where that value that you are writing corresponds to some correctness property that I may be able to write in Hall using real numbers, using the axiom of choice, using all sorts of other
Hey, Dom, just a heads up, you're running quite a few minutes over time, so
okay, I'm just going to
speed up for questions. Yeah.
Yeah, I'm going to skip forward to the end. Okay, so yeah, essentially why we're interested in this is because we've got a project called Veracruz, which is something akin to like multi-party computations, whereas instead of using cryptography, we're using trusted hardware, and the computation is sandboxed with WASM. And the program itself that kind of powers the computation might be sensitive. It might be some sort of IP, for example, machine learning IP. We want some way of bounding the kind of the behavior of this program. So supervisionary might help there. So yeah, just coming to the very end of my talk. So both LCF and desktop OS kernels are both tasked essentially with the same thing, if you squint hard enough, namely protecting system invariants. But the way that they do that is very different. The supervisionary is our experimenting structure in a proof of system, more like a typical OS. We think that this has a number of interesting effects that we're really only now starting to kind of explore. And if you do want to get involved, then please go to the GitHub repository, and pull requests and so on are very welcome.
All right, thank you so much, Dominic.